So let's take a look at electric power with this video here. Power, if you remember, is just the rate at which energy is used. So when we talked about power before, we talked about the energy over the time, right? And we did the units for that, so you might have had like 10 joules used in 2 seconds. And that would give me 5 joules per second, which would give me 5 watts. Alright, so you get 5 watts of power in that example there. So electric power is the rate at which electric energy is simply converted to other forms of energy, or the rate at which the electrical energy is used. So when we do electrical power, we see the power is equal to the current running through this circuit or the device times the voltage across that device or on the circuit. So again, that's current, and that is your voltage. And so electrically speaking, you might be familiar with watts in terms of light bulbs, right? We could have a few little light bulbs right here. Say we have a 40-watt light bulb, and we may have here a 60-watt light bulb, and it looks kind of like a balloon, and a 100-watt light bulb. So each of these, in terms of watts, we're talking about using 40 joules per second of electrical energy, converting it into light and heat energy. Here we have 60 joules of electrical energy every second, and here we have 100 joules of electrical energy being converted every second. So you're probably familiar with the idea of light bulbs. The 100-watt is typically the brightest of these three that we're looking at. And so most light bulbs, you talk about the wattage of the bulb, or the power that it uses. So it's basically how much energy is it using over time. So the one that uses the most energy is the brightest, for example. Alright, so if we look at our circuit that we used in the lab, we had our 5 ohm resistor here and our 10 ohm resistor. We had 18 volts of potential difference. We had the current flowing around through the circuit. We had a current of 1.2 amperes. So the power of this circuit was the current times the voltage. So the power was 1.2 amperes times the 18 volts. That gives the power of 21.6 watts. So how did I get watts, you may ask? So let's look at our units here, our current units of amperes and our units for voltage. So an ampere is simply the amount of charge that flows, or coulombs, per second. Right? So that's our current flow, coulombs per second. And our volts, when we talked about electric potential, is a amount of energy, joule, per charge, coulombs. So we multiply those two together, you get a coulomb per second times a joule per coulomb. And those coulombs cancel out, leaving you with a joule per second, which is a watt. So we have our parallel circuit that we used, and we had a 5 ohm resistor and a 10 ohm resistor, and we had our 18 volt source still. And so this one here, we'll try something a little different. Let's look at this one and see if we can't tell then which of these two resistors here, which of the two light bulbs used more power given this setup here. So we know we had the current flowing through here was 3.6 amperes, and the current flowing through the 10 ohm was 1.8 amperes. So if we wanted to find the power of the 5 ohm, for example, that would be the current, 3.6 amperes through that light bulb, times the 18 volts. And that would give us about 64.8 watts. And then the power of the 10 ohm was its current, 1.8 amperes running through it, and still 18 volts. Remember that the voltage source is the same for each path on a parallel circuit, and so we get about 32.4 watts. Right, so in this case, the less resistance gave us more power here in this case. It was using more energy. We had more current flowing through it as you look at that. So you can look at the power of the individual pieces as well as looking at the power of the total circuit itself. So anything that you look at electrically that has something in terms of watts, you're dealing with the electrical power. How much electrical energy is it using over seconds?